Now let's talk about shadow price. Shadow price is the change in the optimal value of the objective when the right side of some constraint changes by 1 unit. In other words, shadow price is the marginal contribution of a constraint to the objective. This implies that a shadow price is always associated with a constraint. In our Blue Ridge example, there are 3 shadow prices, each associated with 1 constraint. There's also allowable increase and decrease associated with each constraint. However, their meaning is very different from the meaning of allowable increase and decrease of an objective coefficient. We have to be very careful about that. If the increase in the right side value of a constraint is less than or equal to its allowable increase, assuming everything else being the same, then the original shadow price of this constraint is still valid. Similarly, if the decrease in the right side value of a constraint is less than or equal to its allowable decrease, assuming everything else being the same, then the original shadow price of this constraint is also valid. Let's switch to the sensitivity report of the Blue Ridge example and take a look. I will use pump constraint as an example. The shadow price of pump constraint is $200. That means if there's one more pump, the optimal profit will increase by $200. Here, I want to bring one thing to your attention. When there's one more pump, the optimal solution will be different. That is, 122.78 will no longer be optimal. We'll see how to find the new optimal solution a little later. Similarly, if there's one less pump, then the optimal profit will go down by $200. The allowable increase and decrease of pump constraint is 7 and 26 respectively. That is to say, if the total number of pumps is between 174 and 207, the shadow price of pump stays the same, $200. Now, you may wonder why the pump shadow price is $200 and its allowable increase and decrease is 7 and 26 respectively. Let's once again look at the graphic demo of our Blue Ridge example. Before we do anything about right side value of the pump constraint, I'd like to ask you to pay attention to the red line, which is pump constraint boundary line, the feasible region, and the green dot, which is our optimal solution. When there's one more pump, hopefully you see that the red line shifts to the upper right a little bit, the feasible region gets a little bit larger, and the green dot, or our optimal solution, shifts to the upper left a little. However, there's one thing that does not change. The optimal solution is still given by the intersection of the boundary lines of pump and label constraints. It's just that the pump constraint boundary line is no longer x1 plus x2 equals 200, but x1 plus x2 equals 201. Now we can solve the two boundary lines for the new optimal solution. x1 plus x2 equals 201 and 9x1 plus 6x2 equals 1566. The new optimal solution is 120.81, as you see over here. And the new optimal profit is $66,300, an increase of $200. That is how we find the shadow price of pump. Next, how about the allowable increase of pump's shadow price? We know it's 7 from the sensitivity report. To see that, let's add more pumps. 202, 203, 204, 205. Every time we add one more pump, the optimal profit increases by 200 until the number of pumps reaches 207. By that point, the optimal solution is still determined by the intersection of boundary lines of pump and labor constraints. At 207, things are slightly different and tricky. You will notice at 207, the pump constraint becomes redundant. That is to say, with or without pump constraint, the feasible region remains the same. Yes, it's true that the optimal solution is still the intersection of boundary lines of pump and labor constraints, but it's also the intersection of boundary lines of tubing and labor constraints. At 207, if we add one more pump to 208, you will see that feasible region and the optimal solution no longer change. The optimal solution stays at 108 and 99, which is the intersection of boundary lines of tubing and labor constraints, and the optimal profit stays at $67,500. That is, the shadow price of pump is 0 at 207 pumps. However, things are a little trickier than that. To be more accurate, there are actually two shadow prices for pump constraint at 207. One shadow price is of course 0, and the other is 200. Because at 207, if you reduce the number of pumps by 1, the optimal profit decreases by $200. A situation like this is called degeneracy of linear program when one of those constraints become redundant. At this point, it is easy to see that the allowable increase of pump's shadow price comes from 207 minus 200, which is 7. What about allowable decrease of pump then? We'll reduce right side value from 200 down by 1 unit at a time. 199, 198, 197, 196. Every time it is reduced by 1, you will see that the optimal profit goes down by $200 until the number of pumps reaches 174. At 174, the optimal solution is 174.0. It is still the intersection of boundary lines of pump and labor constraints, but it is also the intersection of boundary lines of pump constraint and non-negative constraints of x2 greater than or equal to 0. At this new optimal solution, the labor constraint becomes redundant because with or without it, the feasible region is the same. Once again, this is another situation in which we see degeneracy. At 174, the optimal profit is $60,900. If we have one more pump to 175, the optimal profit goes up by $200 to $61,100. That is, the pump's shadow price at this point is 200. But if we reduce the number of pumps by 1 to 173, the new optimal profit goes down to $60,550, a decrease of $350. That is, the other shadow price of pump at 174 is $350. As you have probably noticed, when a resource becomes more and more scarce, its shadow price gets higher because this resource becomes more valuable. Now, you should know that the allowable decrease of pump is 200 minus 174, which is 26. I'm hoping that you can find the shadow prices of labor and tubing constraints and their respective allowable increase and decreases as well. Also, what about the shadow price and allowable increase and decrease of two non-negative constraints? Since pump constraint is one of the binding constraints, let's take a quick look at one non-binding constraint as well, the tubing constraint. I will provide a few observations and leave the details to you. Because the tubing constraint is non-binding, its shadow price is 0. At the optimal solution, we have more than enough tubing. Actually, we have a slack of 168 feet of tubing. So having more tubing does not help and does not contribute to our objective at all. That is why the shadow price of tubing is 0 and allowable increase is infinity. Technically, 1e plus 30 is equal to 10 to the power of 30, a very, very large number. That is how Excel denotes infinity. Here, in our Blue Ridge hot tub example, we have a profit maximization problem. All the constraints are of the less than or equal to type. You've probably noticed that the shadow price of less than or equal to type constraints in the maximization problem is greater than or equal to 0. Now, I would like to ask you to think about the following questions. What would be the shadow price of a greater than or equal to type constraint in the maximization problem? What would be the shadow price of a less than or equal to type constraint in the minimization problem? And what would be the shadow price of a greater than or equal to type constraint in the minimization problem? When two or more right-hand side values of constraints have changed, we also have a 100% rule, which is different from the one associated with the changes in two or more objective coefficients. This 100% rule for shadow price says that if the total percentage change in right-hand side values with respect to allowable changes is no more than 100%, then the original shadow prices are still valid. Let's consider the following situation. Blue Ridge is able to get 3 more pumps from its recycling and remanufacturing program. In the meantime, however, Blue Ridge expects to lose 30 hours of labor due to the coming flu season. What would be the overall impact of these changes on the optimal profit? First, there's an increase of 3 pumps with allowable increase being 7, and there is a decrease of 30 hours of labor with allowable decrease being 126. Second, the total percentage change with respect to allowable change is 3 over 7 plus 30 over 126, which is less than 100%. In this case, we don't need to actually calculate the ratio. It is easy to see that both 3/7 and 30 over 126 are less than 0.5, so the sum of the two cannot be more than 100%. As a result, the shadow prices remain the same. The impact on profit would be 3 times 200 minus 30 times 16.67, which is equal to $100. That is to say, overall, the optimal profit is going to increase by $100.